Ωραία.
Okay. Good evening, everyone. My name is Stamatakis. I'm the current president of SPE Student Chapter, and it's my pleasure to welcome you all to our first webinar of the year, organized by the SPE Student Chapter of the Technical University of Crete. Yannis Tsanas will tell us some information about the SPE Student Chapter later on. I would like to say a special thank you to our faculty advisor, Professor Yotis, and of course to our speaker, Dr. Emmanuel Stamatakis. As we all know, the need for an energy transition is widely shared nowadays. However, the implications and challenges that must be resolved call for a concerted effort. Hydrogen has the potential to be a powerful enabler of this transition, as it offers a clean, sustainable, and flexible option for overcoming multiple obstacles that stand in the way of a resilient and low-carbon economy. So, Hydrogen Energy Transition, the Greek case, is the title of this webinar, presented by Dr. Emmanuel Stamatakis, Associate Researcher at the Institute of Geoenergy-FORTH. I think, Jan, the floor is yours. You can continue.
Okay, good evening, everyone. My name is Ioannis Panagiotis, and I am a member of the TUC SPE student chapter. The TUC SPE is a student chapter which was established in 2018 and consists of students from the Mineral Resources Engineering department. Its main purpose is educational and aims to introduce young students to the petroleum and gas industry. I will give now some information about our host, Dr. Stamatakis. Having a PhD in chemical engineering, a master's diploma in production management systems, Dr. Emmanuel Stamatakis currently holds a research position at the Institute of Geoenergy-FORTH. Previously, he has been working as a research collaborator for various research centers in Greece and abroad for over 15 years in the fields of petroleum research, renewable energy, hydrogen technology, and environmental protection. He has been acting as the main liaison between the industry and the research community on various hydrogen energy and environmental issues during his career, having fulfilled a large number of industrial research programs through his active participation in all stages. Furthermore, he has been involved as a research scientist in various national and international environmental and hydrogen energy projects, such as CHIP-FC, Demo4Grid, Pearl, among other projects. His interests revolve around hydrogen and fuel cell technologies, alternative fuels, renewable energy systems, energy storage, environmental technology, tracer technology, flow processes in geological reservoirs. Dr. Stamatakis, the stage is yours.
Thank you, Ioannis. Thank you, Priscilla, and thank you, Mr. Yotis, for this invitation. And I have the honor to be here and present this interesting topic on energy transition and how hydrogen can support this. And give 1 minute to share also a presentation. Can you see?
Yes.
Okay. As I said, the topic is hydrogen energy transition, and we will say a few words about what is the case in our country and what are the actions that Greece is doing regarding energy transition and the implementation of hydrogen applications. We will also end up with some information about our institute, and of course with questions at the end. This is how I like to start my presentation when I talk about hydrogen. Put it here. It's a part of the novel of written back in 1974 by Julius Verne, Mysterious Island, where it was the first time that hydrogen was referred as actually the fuel of the future. Cyrus Harding was the imaginary hero of Jules Verne. Actually described this.
Mano, sorry to interrupt you. We cannot see the slide. I cannot see the slide.
Cannot see. Okay, what can you see now?
The first slide only, hydrogen in energy transition.
Okay, I have
the Greek case.
For me, it works. It goes to the second slide.
Liana, do you see the?
Okay, I will stop sharing and I will put it back again to see.
Yes,
I see
maybe
only the first one.
Yes, yes. Maybe if you share your entire screen, it will work. I'm not sure, but
let me. Okay. If I put it like this, but it's not.
I see now the second one.
Yes, but this, yeah, it's working, but it's not a slideshow. But okay, we can leave it like this. Okay, just to be sure. Okay, this is, as I said, how I start my presentation, and this is a part of the novel of Jules Verne, written in 1974, where it was talked about the first time ever that hydrogen can be the future energy fuel. Almost 150 years later, hydrogen economy is about to become a reality. Very recently, 2 years ago, there was a lot of announcements from the European Commission regarding how hydrogen can could be introduced as an energy carrier in our energy mix. And a detailed hydrogen strategy has been announced, and a lot of funds have been already guaranteed on this hydrogen strategy towards the next 20 years period in order to demonstrate some large-scale hydrogen projects in various applications, both for stationary and transport applications. A short overview of what we are going to discuss today is to see what is the reasoning behind seeking of alternative fuels, and how hydrogen can play is acting as an energy carrier, how it's produced, and what kind of industries are using it today, how we can store it and transport it, and we will talk about vehicles that utilize hydrogen, if they exist today, how hydrogen empowers the energy transition, and what is the case for Greece. And as I said, we will end up with a few words about the Institute of Geoenergy and our activities on hydrogen technologies. This is something that probably all of you are familiar with. These are the new key targets of the European Union regarding for 2030 regarding greenhouse gas emissions, where the promise is to have at least 40% cuts in greenhouse gas emissions compared to the 1990 levels, and at least 32% share of the renewable energy in our European energy mix. Regarding the transport sector, specific target as 30% decrease of CO2 emissions by 2030 and 6% decrease of CO2 emissions by 2050. Very few words about hydrogen because you are all engineers and familiar with this element. It's the first element of the periodic table, recognized for the first time as a separate element in 1776. Even though it's the most abundant element of the universe, at least 75% of the universe is hydrogen. On the other hand, it's very rare in its elemental form on Earth. And for that reason, we need energy to produce it. Here is some hydrogen demand by industry, the industrial sector. The industry uses hydrogen for a lot of decades for various applications. The chemical industry is actually the most intense energy hydrogen user, for instance, for ammonia production, for polymers and resins. Then is the refining sector for hydrocracking and hydrotreating. And then comes the iron and steel industry, cement industries, and some other industry like food industry. Typical clean hydrogen, typical hydrogen production options are the ones that you can see in this slide. The first one on the top is the green hydrogen production option, where hydrogen produced by renewables using water electrolyzer, where hydrogen can be split where water can be split in hydrogen and oxygen with renewable energy. And on below you can see the blue option of hydrogen production, where hydrogen can be produced from fossil fuels like natural gas using, for instance, SMR, steam membrane reforming. And then it is a blue only when the CO2 that is produced from with this option, you capture it and you store it. If you don't, if your CO2 is you leave it in the air, then the option, this hydrogen production option is called has a gray color. As you can see, about almost 95% of the current hydrogen production options is coming from fossil fuels. And for that reason, back in 2019, almost 830 million tons of CO2 were produced for the production of hydrogen. A few words about the steam methane reforming. It's the most common and the most easy method to produce hydrogen from fossil fuels. This splits natural gas into CO2 and CO mixtures, and hydrogen, of course. Various industries use SMR technology to deliver large quantities of hydrogen and carbon monoxide and carbon dioxide being released to the atmosphere. The process is very mature, with systems capable of producing up to 100,000 of metric tons per day of the mixture of hydrogen and carbon monoxides. Currently, over half the world's hydrogen is derived from natural gas reforming. When SMR is combined with carbon capture technology, then, as I said, hydrogen is recognized as a blue hydrogen, and this is something that a lot of demo projects are being developed worldwide. This is a project now operating in UK, where large quantities of hydrogen are produced from natural gas, and the CO2 is captured and stored at the ground. For hydrogen storage options now, there are three main ways to store hydrogen. One is as compressed gas. By compressed hydrogen, the volume it occupies is reduced resulting in higher energy density per volume. We can store it as a liquid, but this is since hydrogen will be liquefied, you have to reach minus 253 Celsius. So you need a lot of energy in order to liquefy hydrogen and store it as a liquid. And there are some other cheaper methods like chemical storage, where you can, for instance, store hydrogen in the form of ammonia or in solid storage, like store it in metal hydrides. We are not going to say more details on this, but at the end you can ask me if you want any questions regarding those technologies. What is very interesting, and also for your background, is to store hydrogen in large quantities in geological formations. This is what now the research community, and not only, also the industrial community is looking, is to store hydrogen in salt caverns at the ground. Some big salt caverns have been identified but not certified yet all over the Mediterranean Sea, and there are also some big salt caverns, potential big salt caverns south of Crete. And this is something that we will start looking also as an institution to store hydrogen in those geological formations. For transporting hydrogen from one place to another, this is very connected to the form that you have already stored. So you can transform it either as a liquid or as a gas using the conventional transporting systems that you can see in this slide. Another interesting, of course, transportation system is through the existing pipeline, natural gas pipeline network, where you can, let's say, inject hydrogen in various mixtures in the existing natural gas networks and transport them to various places. And of course, the idea is to make those networks pure hydrogen transportation in the future. The hydrogen is an ideal element to store renewable energy, and this is why we call it as an energy carrier. Because when you produce hydrogen from renewable energy systems, you can store it and you can have it as long as you wish, and use it for instance after years by taking back the electricity that you have stored in hydrogen form. You can use also hydrogen in natural gas grids and industry, as I said before, and to electrify it both for stationary and transport applications using fuel cell systems. But we will say a few more things later. What is important to say here is that the technology for both hydrogen and fuel cell systems exists and it is mature. The only problem is the necessary infrastructure that has to be constructed in order to transform our society into a hydrogen economy. Vehicles that are using hydrogen exist a lot of years now. The first one, you can see it was the first internal combustion engine utilizing hydrogen back in 1807. this is one of the first cars that Volkswagen produced more than 20 years ago. NASA is using hydrogen for various applications in the space industry. And we have already hydrogen trains and hydrogen buses all over Europe. For instance, if you have visited Hamburg in Germany, most likely you have been you have used a hydrogen bus because it's all over the city, and for many years now. An early market for hydrogen basically is the forklift market. It's quite easy to transform the conventional forklifts into hydrogen vehicles, and it was one of the first projects in the US, where now more than 5,000 forklifts are hydrogen forklifts are being used in the logistics centers in US country. These are the top 3 hydrogen cars that someone can buy. Even you can buy it, even though that unfortunately in Greece you cannot have it, you cannot use it because at this stage we don't have a regulated framework of driving hydrogen cars in our country. However, if you go abroad, in almost all European countries, and mostly Central European and North European countries like Belgium, Netherlands, Germany, UK, etc., you may see those cars running around. For instance, the Toyota Mirai that you can see, more than 500 taxis in Paris are hydrogen cars, Toyota Mirai cars. You can see here they have a lot of quite high autonomy, more than the Hyundai Nexo is more than 600 kilometers. And they have they need around 5 kilos, 6 to 5 kilos of hydrogen in their reservoir. Here we are now regarding the refueling stations that exist in Europe. Unfortunately, as you can see, only in the Central and North Europe there are some refueling stations that someone can take his car and refuel it in those stations. And the plan is, this is a plan that the commitment actually of various countries for the next 2 to 3 years, more than 750 new hydrogen stations will have been announced for 2025, and again, unfortunately, not for Greece. Even though that we have already our institute also participate in some committees in the country, and we have already asked for a number of hydrogen refueling stations for Greece in the coming years. Now, we need to understand the risk and the barriers regarding the fuel and how to implement hydrogen in the country. Location and accessibility of the site and fuel supply is very important. Currently, few commercial models exist and slightly more variants of buses and trucks. So this is something that they call it the chicken and egg problem. We have a technology here. We have the car industry is ready to put cars and heavy-duty vehicles on the road. but they expect for this map to enlarge and have as many as possible refueling stations. And from the other side, no one takes the risk to build hydrogen refueling stations before a critical mass of cars, hydrogen cars, are on the road. So here has to come, let's say, the government and the politics to take some decisions and try to help to build the necessary infrastructure and start, let's say, creating some critical masses for introducing more and more hydrogen applications in various sectors. An important part of hydrogen and its application is how it can empower the energy transition. And this is actually the topic of the today's discussion. As you can understand, hydrogen it's a clean energy carrier, it's safe, even though someone may disagree on this, but indeed the safe, it's so safe as it is using, for instance, natural gas. And natural gas is quite common, and everybody now uses natural gas for both for heating their apartments or in their cars. For instance, in Athens, a lot of natural gas cars are on the roads of the city. Hydrogen can be, as I said, can be transported over long distances, allowing the distribution of energy between countries. This is very important. It produces clean power and heat for transportation applications. Can be produced without a carbon footprint when you have the SMR together with the carbon capture option or from renewables, of course. Has a high energy density that makes it very suitable for long-term storage. It is required as a clean feedstock in the industry when recycled, when CO2 can be captured. The EU position on hydrogen, which, as I said, is very recent. This was announced that you can find the report in the full report of the hydrogen strategy of the European Commission in this link here. They expect that from 2030 onwards, renewable hydrogen will be deployed at a large scale across all hard to decarbonize sectors. Until then, they expect to have a mixture of blue hydrogen that produces CO2, or even and capture for the CO2, or even gray hydrogen that CO2 is emitted in the atmosphere. How can hydrogen be promoted in Europe? This is an outline from the European Commission hydrogen strategy. The first is that the production of clean hydrogen needs to be increased by creating a sustainable industrial value chain. We should boost the demand for clean hydrogen coming from industrial applications and mobile technologies. Clean hydrogen needs a supportive framework of well-functioning markets and clear rules, as well as dedicated infrastructure and the logistical network. By promoting research and innovation in clean hydrogen technologies is very crucial. Europe will secure cooperation opportunities with neighboring countries in the region of the United States, of the European Union and work to establish a global hydrogen market. This is happening actually, and there's discussions now with North Africa and some Asia countries on this for large-scale production and uses of hydrogen between those areas. And finally, the European Clean Hydrogen License that was announced 1 year ago will help to build up a robust pipeline of investments. And the first calls for funding are expecting in this spring from the European Commission. This is what expects by 2050, what the European Union expects by 2050, that hydrogen can enable major CO2 emission reductions in the order of 7.5 gigatons annual CO2 reductions by 2050. Supporting this energy transition, there are a lot of big initial applications all over Europe and all over the world. This is a UK scenario where they produce large quantities of hydrogen offshore and by SMR technology, and they capture CO2 and they store it underground. And then they transform hydrogen, you can see it here, they produce electricity offshore and they transport it to the mainland. This is something that has been start building, as you can see in the pictures here, and they expect to have it fully operated over the next 5 years. Sorry, I will go to the next. This is another example from the Rotterdam city, where Rotterdam has decided to transform, to be transformed from global oil and gas hub to a hydrogen hub. They have already started this, and they will follow a similar approach to the UK scenario. They will produce from offshore renewables, wind offshore, large quantities of hydrogen, and at the same time they will also produce offshore hydrogen by using natural gas, and they will try to store both CO2 and hydrogen underground for large scale underground storage. And then when necessary, they will transfer hydrogen back to the country for various applications, for industrial sector, for residential sector, for heating purposes, and for the transport sector for both heavy duty and light duty vehicles. This is the recent announced Houston Hydrogen Hub Vision, which again is a similar approach like Rotterdam and UK for large-scale hydrogen production offshore and onshore in this case. And before going to what happens in our country, I will give you a short summary of who we are and what we are doing on hydrogen technologies, and then we will explain a few things about the case of Greece. As you may know, our institute was initially formed as Institute of Petroleum Research back in 2019, and a few months ago was renamed to Institute of Geoenergy. We are using the premises of the School of Mineral Resources Engineering. But in the near future, we expect to have our own buildings, again in the campus of Polytechnical School of Crete. And this is how we have designed our new buildings. It's buildings of the order of 3,000 square meters over a place of more than 30,000, I think, square meters, if I'm correct. Okay, it's not necessary to say something here. Our mission is high operating standards and research excellence, credibility in the scientific community and in the energy industry, and to be a reference point is a Geoenergy Science Center. And this is our new scientific directions, our new divisions that we have decided. The first one is the fossil fuel direction. And here we have added the carbon management. This is oriented to the research and the development of methods and techniques for exploring geological structures suitable for the generation and production of fossil or carbon-genic energy resources, the development of innovative methods for their production and transport, the production of conventional fuels with minimal carbon footprint, and the development of technologies for carbon dioxide capture and storage. So here we have both fossil fuels and CCUS technologies. The second direction is the environmental and circular economy, which is oriented to studying and developing innovative methods and techniques addressing the environmental impact of energy resources exploitation, including fossil fuels and green energy installations, monitoring, assessment, and mitigation of environmental pollution. And a big part is the circularity of this, of all of this. It also aims at the development of materials and energy reuse technologies and the elaboration of environmental impact studies and energy exploits risk assessment. And the final sector where I'm actually working on is the green energy sector, which is oriented to the development of innovative technologies related to the reduction of carbon footprint of the energy mixture using hydrogen, geothermal energy, and other green fuels like biogas, ethanol, ammonia, etc. And the optimization of the energy system structures and operation. This is our people in our team. Professor Yotis is also an affiliated member of our team. We have already established a network of supporters and partners with active sponsorships. One is from the Hellenic Petroleum, where we have a 5-year support sponsoring agreement already in place, and the second and very recent one is with the Motor Oil Group, which supports especially the sustainable and fair energy transition by promoting research and innovation of this field. So Motor Oil is sponsor our work only on energy transition, the energy transition field. We have from today actually a hydrogen laboratory. Unfortunately, we didn't have the time to take some pictures where we have a small hydrogen electrolyzer that produces 24 liters per hour of hydrogen, storing hydrogen in a metal hydride tank. Then we have a fuel cell stack in the order of 500 watts to re-electrify hydrogen and produce electricity with a high precise edge-to-gas flow meter to take some measures, and a load bank that operates between 0.1 and 1 kilowatt in order to simulate the demand side of electricity and simulate the whole system. And we have some various computer models like Homer that you can simulate various hydrogen scenarios. And this is a facility that we expect to attract students like you to make some their thesis or studies in the near future. We have already 2 active hydrogen projects, one with the region of Western Macedonia, where we act as their official consultant on how hydrogen can be introduced in the region to support the decarbonization. And a new one that is about to be signed with the Regulatory Authority of Energy in order to support the regulatory framework of hydrogen in the country. And speaking on that, this is the long-term outlook on hydrogen technologies in Greece. The first priority is to develop a roadmap for real-scale deployment of hydrogen and fuel cell technology in the country. And this is something that we also participate as an institute, since I am a member of the National Hydrogen Strategy Committee. And this roadmap is about to be launched for consultation, for public consultation, so everyone will be free to make comments on this roadmap before being officially adopted by the government. Another bullet is that as a country, we have to support training and educational technologies in various hydrogen applications. So through especially collaboration between the various research centers and the academia of Greece, and try to create a national hydrogen cluster. This is something that we also try to accelerate as an institute, and we are trying to establish collaboration with. We have already established some collaboration with the National Center for Scientific Research Demokritos, with universities like Technical University of Crete, with various industries like motor oil, petroleum, as I said before, and various SMEs. So the next step is to try to formulate this in a Greek hydrogen cluster. A third priority for the country is to try to attract private financing for deploying large-scale hydrogen projects. This is something that has to be done very carefully. The money, let's say, are here. The Commission has secured a lot of money for this kind of large-scale hydrogen projects. And but without a Greek national roadmap that explains what our country wants to do on hydrogen technologies, you cannot go and ask for money. So we have to have a concrete plan of what we want to do on this field, and then the money, let's say, are waiting to attract them. And finally, what we need is to disseminate and promote this technology to the commercial sector, but also very important to the public and the citizens, and try to engage local and regional stakeholders for large-scale implementation of hydrogen projects. And again, our institute is working on that direction, and has a lot of bilateral meetings with various stakeholders, starting from the local community, Chania, and the regional community for the region of Crete, and also national stakeholders, since we are in close communication with various ministries and trying to assist on the finalization of the regulatory framework for introducing hydrogen as an energy fuel. Greece, and this is something that we have to say, has some special characteristics that could create sustainable value chains on hydrogen applications. The first one is that it has a very high renewable energy capacity, and this means that you can produce green hydrogen without CO2 emissions, very easy. There is a lot of industries, important industries exist in the country that uses and they need hydrogen for their applications. For instance, the refineries, the chemical industry, the metal industry, and the cement industry. So if we give them clean hydrogen at low cost, this is something that they are ready to take it. The insularity of the country with important passenger and commercial maritime transport and shipyards, in combination with a leading position of Greece in the shipping sector, because the shipping sector is now, over the last year, is driving the hydrogen application, since a lot of projects, large-scale projects, are active right now, trying to build real-scale ships and shipyards and ships and boats working on hydrogen or other alternative fuels like ammonia. We have a region's transition like Western Macedonia, and hydrogen can help their complete decarbonization. Large sections of the country's railway network have not been electrified, and this is why this is important, because the target, and this is something that the European Commission actually has put as a priority, is all railway network of the European Union has to be electrified and stop using fossil fuels for the trains. And it's not so easy to put electricity in the railway, but it's very easy to make it electrical trains by using hydrogen. So you use the existing railway network, and you only change the train that runs on hydrogen, which you make it electrical with actually no CO2 emissions. There is a significant infrastructure in gas transmission and distribution networks in the country that can be used with relatively little additional cost for injecting hydrogen mixtures and transporting hydrogen through that network. And in the near future, it can be fully converted into pure hydrogen networks. The experience here is that this has been developed in matters of development and management of energy markets, also helps in this direction. And all over the world, they are now developing nodes and to inject hydrogen in the natural gas network. And DESFA, the Greek natural gas regulator, is also has developed a study of how to do it, and this is something that we will see it soon. Also, the country is highly active, has highly active research and scientific community in the field of hydrogen for a lot of years now. Actually, Greek scientists were among the first ones in Europe that started working on hydrogen technologies. And there is the ability to develop a separate commercialized products and components, technologies, and services throughout the whole hydrogen chain. And this can create possibility to activate startups and spin-offs, and this is something that we see that it's happening. A lot of new startups companies are formulating the last few years and start looking hydrogen, putting hydrogen in their portfolio. And I think I will end up with our vision as an institute, probably it's also my personal vision, is to create the first hydrogen highway here in Greece. It's a big opportunity to make VOAC one of the first hydrogen highways in the country. It's not, it will not be the first highway in Europe or in the world, because this is something that exists already in Europe. But this is a plan for our country, and this proposal, you say, it will be part of the roadmap that is being developed, the national roadmap, and they will propose to make VOAC the first Greek hydrogen highway. So the plan is to install at maximum at least five, not maximum, at least 5 hydrogen filling stations among VOAC in various connection nodes, so it will be close to the ports and the airports of the road. In that way, and we are in contact with CTEL and municipal authorities to introduce at least 20 hydrogen buses and a number of hydrogen trucks to use those refueling stations. So we hope that we will have some good news about this in the coming months. Thank you for your attention.
Thank you, Dr. Stamatakis, for this very interesting presentation. I'm sure this webinar clarified the value of hydrogen in the energy transition. For me, it sure did. And let's now move on to the questions. You mentioned about a project in Western Macedonia. Is that the White Dragon project?
Yes and no. Actually, White Dragon, it was something that was formalized over the last years. We are, let's say, we are consulting Western Macedonia of how to introduce hydrogen in their energy mixture, and not only on White Dragon, yes, but it also refers to the White Dragon.
Okay. What do we mean when we say that hydrogen is an energy carrier? Where does the energy come from?
Hydrogen is not a primary energy vector, okay? It's not, you have to produce it. So that's why it's an energy carrier. It's like a battery. It can store energy. That's why we call it energy carrier. And hydrogen, when used, you can take back its energy as in electrical form, very easy and very quick. So let's, for instance, in fuel cell systems, actually a fuel cell system is the opposite of electrolyzer. It takes hydrogen and oxygen from there, and it produces water and electricity. So that electricity you can use it either on a car, on a vehicle. So actually, it's a hydrogen car. It's actually an electrical car with an electric motor, or for stationary applications using the electricity. For instance, if you have a renewable park, or a wind park of PV, and you don't have wind or solar energy, then the stored hydrogen can be used to give you back electricity to the system.
Okay. Some questions from the people who are attending the webinar. Hello. As we know, hydrogen has a small molecule, so it can be easily integrated in pipes. So it is a big risk to transport it. How can we eliminate that risk?
Sorry, can you repeat the first part of this question?
Yes, as we know, hydrogen has a small molecule, so it can be easily integrated in pipes. So it is a big risk to transport it. How can we eliminate that risk?
I cannot understand this question, but okay, if I can say is the hydrogen is the lightest element. Okay, in order to transport it, you have to compress it. But this is similar case with natural gas. The big pipelines, the big gas network transport, for instance, TAP, that is now constructed, transform natural gas at 90 bars. Hydrogen will be also transported through pipeline network at almost at the same pressure, around 90 to 100 bar. I think the safety aspect from this matter is not an issue, because it's well known how to handle hydrogen, and this is, as I said, hydrogen is being used by the industry a lot of years now, so we know how to handle it. It's almost similar to handling natural gas.
If I may add to the question, maybe he meant to say that the molecule is so small that it can escape practically from any tank. As you know, and, as I also know, you need to store hydrogen in under very specific conditions, even when compressed in vehicles. And even in this case, it manages to leak off, to escape. So there are scenarios.
As liquid, but as gas, I don't think so. Now I think they have solved how to store the hydrogen on vehicles as compressed. It's quite mature, the technology, and I have not seen any leakages on compressed hydrogen. Recently I visited Austria, that they have a refueling station, and for a project, and I had this Hyundai car that I showed you before for a week. I refuel it the first day, and after a week, I had same hydrogen in the deposit. So I don't think that we need to worry on this regarding how to store it on board, at least. As a liquid, yes. As cryogenic liquid, there you have this boil off, and because you cannot keep minus 250 degrees Celsius the deposit very easily, and if the temperature increases some bit, and you have this boil off, and the system has to release hydrogen in order to keep it there. So yes, there you lose it. As compressed, I think now we are. I think now we don't have any issue on this.
Thank you. Maybe Ursula wants to add something. I see you've raised your hand.
Yes. Firstly, Mr. Stamatakis, thank you very much for the excellent presentation. I have a question. I saw the different types of storage. And I would like more information about chemical storage, if it's possible.
There are various chemical storage options. One, let's say, it's let's say, transform hydrogen to other chemical substances like ammonia. Ammonia, it's easy to produce it from hydrogen, nitrogen, okay, from the atmosphere. So this is a way, and ammonia actually is something that they look already, various industries, as an energy carrier that contains hydrogen. So you can transform hydrogen to ammonia, and then you can take it back or use ammonia as it is. This is an option. Other chemical storages is, for instance, the so-called liquid liquid organic hydrogen carriers. There are some liquids that they can absorb hydrogen. They change a little bit the structure, but they remain liquid. They are organic liquids, okay? They are organic liquids, and by heating them, they absorb hydrogen. Then you can carry them as organic carriers, liquid organic carriers. This is very easy to do it because you don't have to change anything regarding the transportation methods. You use the conventional methods to transport, like you transport oil. Okay? And then again, easy, you can take back the hydrogen from this carrier, but you can understand that you need extra energy to make it liquid and take it back. So someone has to consider all these options and see if this is cost economic to do it and which method to use.
Okay, thank you very much.
And next question, why should we go to hydrogen for our energy consumption and not ethanol?
Because if we say that we need to go to a zero energy system, a carbon-free system, then ethanol, when you burn ethanol, you have CO2 emissions. So, but the ethanol, yes, it is probably something between. It has lower CO2 emissions, of course, compared to oil and gas, but again, it has CO2 emissions. So the only fuel now that has no CO2 emissions is actually hydrogen, and it's energy carriers like ammonia.
Okay. Next question, how feasible is the production of blue hydrogen with respect to carbon capture storage and storage in large scale in particular?
This is a good question. This is something that if your colleague asked that question a few years ago, I could say that this is not feasible. But what we see now over the last few years is that for real large-scale projects, it becomes very feasible. And this is something that US is starting building a lot, and a lot of North European countries.
Is there a critical point in terms of temperature, pressure, as in CO2, to achieve the best underground hydrogen storage?
I'm not so familiar with that field, so actually I cannot ask. I don't know if Andreas can have know something on this. But this is something that my colleagues here, who is a geologist, start looking for. So I'm not so familiar with underground hydrogen storage. So I cannot answer that question.
Mm-hmm.
But definitely there will be some special limits and some special characteristics that we have to follow.
Personal question that I would like to ask. You mentioned earlier about the DESFA, the Hellenic Gas Transmission System.
Yes.
I made my internship last year in summer there, and I saw about the pipeline for hydrogen through Bulgaria. They are planning to construct, or there's already started.
They
What do
are
you
now
know about
starting
that
a new
project?
one that will go from Revithousa to meet TAP. And this is something that SNAM, the Italian regulatory, once asked actually from DESFA, because SNAM is shareholder of DESFA. And the plan is to install a Revithousa hydrogen production plant and inject hydrogen in that network and go to TAP. And the Italians now are ready to receive hydrogen through TAP.
But in Revithousa, I think 2 years ago, or last year, they completed the construction of the third tank there. Can they transform these tanks from LNG tanks to hydrogen tanks? Have they the same?
Look, all the infrastructure, this is something that is they are obliged to do, are hydrogen ready. All new infrastructure, pipelines, etc., have to be hydrogen ready. Otherwise, we don't take any loan from any bank around the world. So even also TAP is hydrogen ready, can take hydrogen, either pure hydrogen or mixture of hydrogen and natural gas. And this is the study that we did for DESFA a few months ago, to make the whole network hydrogen ready, or also the old one.
Okay, thank you very much. There is one last question here in the chat. Could you please talk about the use of hydrates for the storage of hydrogen?
Professor Stamatakis will be the most, I don't know if he's here with us.
This is a very big issue.
It's
it will take time.
Issue. But if you are interested, we want to make some project on this, and we have some proposals of how to do it. But it's a big question, yes. But it's possible to do it, but it needs a lot of research.
Okay, thank you. If there is anyone who wants to
I would like
question,
to
make a question,
ask,
raise your hand, please.
Can you hear me?
No, yes.
Okay. So first of all, I want to thank Dr. Stamatakis for this very nice talk and the advertisement of the institute, of course. Obviously, we know each other many years, so I know that he's an expert in this field. So he is the best person to talk about hydrogen in Greece. I also saw in the chat that there are some faculty members of the school. Professor Passardakis was watching the talk. Also, Professor Varoufakis from our school, Dr. Antoniou. I would like to thank them as well for their time and their presence. I see Professor Varoufakis here, so thank you very much. We are trying to support the actions of our students, and by organizing these seminars and the help of speakers like Dr. Stamatakis, I think that this is very, very important and very it offers a different, line of skills for our students at the school. So this is actually quite important for everyone who is participating. Then, after this short comment, I would like to ask a question regarding the relevance of hydrogen as a potential energy carrier compared to batteries. So from your talk and what I know from personal experience, hydrogen has many bottlenecks to overcome, many thresholds to overcome regarding production, regarding storage, regarding transfer. In any case, obviously, it is a high-density energy carrier, okay? This cannot be argued. But what is the strategic advantage of this form of energy compared to the electrification that it is currently ongoing, and it is actually now, here and now, happening as part of the energy transition and the decarbonization of our society. Especially, this starts with lighter vehicles. I understand this, but I see this going at a faster pace every day. So some data is that I read the sales, the statistics, the data from the sales of cars in Greece, and 2021 was like electric cars. It was like a magic year for hybrids and electric cars. Even Tesla, who has no technical support in Greece. So if you buy a car and it breaks down, I don't know what happens. Even Tesla is selling like 500 cars, sold 500 cars in Greece in 2021. So what is the extra that hydrogen has to offer, given all this limitation? Is it a technology, according to your opinion, that it is the next step, or it can clearly compete with battery?
It's well, very good question. This was actually a debate over the last years regarding let's say, battery electric cars and fuel cells electric cars. Well, for me, at least at this stage, it's not a compete. It's something that can run in parallel. It's not the next step. We don't see that batteries can be used in heavy-duty vehicles, for instance. We know that, I'm not the one that is supporting this. I was recently just before the COVID issue, I was in Brussels, and the CEO of the Heavy Duty Vehicles Association globally said that clearly that the only way for heavy duty zero emission is hydrogen. No other technology exists. Because no heavy duty vehicle driver wants to wait even 20 or 30 minutes to, let's say, to recharge his battery truck. That will take at least more hours than that. And as it is a technology now, get the batteries, they need one more truck to transfer the batteries that they need in order to run the vehicle. So it's not feasible at the moment. And this is not, if this is something that even Elon Musk recognized, but not on camera, but behind cameras. And the big project that for battery trucks has been stopped. And actually, Elon Musk is doing. They have a new company that they don't call it Tesla, that start producing hydrogen trucks. Okay. The other question is that, and I can show you here also a study from Germany that was from the German government a few years ago, because you should about some bottlenecks regarding hydrogen production, but there are no bottlenecks there. The technology is here. Okay, it's who pays the money in order to install it. Regarding the infrastructure, this will come also for battery cars, because okay, now we start seeing, and I also would like to buy a battery car, okay, in Athens. But imagine how many are now. Do you remember the numbers? It's around 1,000. I think 1,000 cars in Athens.
I think it was like a couple of thousand last year. So.
Yeah, below 10,000. Yes.
Yeah.
Imagine 500 or 1 million.
It's a big increase compared to 2020. So this is
imagine 500,000 or 1
be
billion cars running on batteries in Athens. We don't have the network to support it. Okay,
the same goes for hydrogen. So it's
no.
We don't have the network.
Correct. We don't have the network. So again, this is what I wanted to say is that the network is the problem, and this will also become a problem for batteries if everyone start buying a battery car. And the study, I have it in this presentation. I have it, but I didn't show it. I can do it. I think it's here. Yes. Okay. This is a study that the Germans made a few years ago with a scenario of the introduction of battery cars and hydrogen cars in the country. And there is some point here that they see, they believe that the costs of creating the necessary infrastructure for battery cars will be much higher regarding fuel cell cars. Okay, this is the base case is 51 billions for. This is the limit is here. It's 10 million electric vehicles. So if in Germany more than 10 million electric vehicles introduced in the country, then the infrastructure for hydrogen is lower regarding the necessary infrastructure for batteries. Okay. But as I said, for me, this is not an issue because what I would like to see is battery cars for cities, light-duty vehicles, and hydrogen cars for heavy-duty vehicles. And then probably the future will be for families, 2 cars, one battery car as a city car, and one hydrogen car as your car for going vacations.
I think I agree with this point. Diversification of the energy grid. You need to have multiple types of energy and not rely solely on fossil fuels like 80%.
For me, it was never this a competition between those. I want to see both. Okay.
Thank you.
May I add that we may not have the infrastructure now, but would it be possible in the future? Yeah, Dr. Stamatakis.
The infrastructure is start creating. Now it's again who pays, okay? This is the question. And we need a strategy on this. And we need a strategy of what kind of infrastructure we need. Let's say, let's start from our country. Because we have to take some scenarios to see if indeed more than 500,000 cars, electric cars, are in Athens over the next decade. What kind of electricity infrastructure is needed to support that? Chargers, fast chargers. You know let's say the experiment of that big Elon Musk with the Tesla and the new fast charger in California, or in Alabama, I don't remember where. That they develop a fast charger and battery for the Tesla car, and they say that we will charge it in less than 20 minutes. He did it. But then they had a blackout in the whole region. Okay. So
Thank you very much. Does anyone want to ask a question? Please raise your hand. I think not. Okay. We want to thank you once more, Dr. Emmanuel Stamatakis, for this presentation and for this webinar.
it was a pleasure. Thank you.
It was very interesting. I want to thank you all for attending today our webinar. And I will stop recording now.